Okay, thanks. So actually, this is a great pleasure. It's actually the second time I've seen Eli this week. We had a very successful review of our Energy Frontier Research Center. And apologies for missing you this morning. Two of the planes I was on early, my first plane I was sitting on at 6 a.m., the first two broke down, and the third one actually circled over SFO for an hour. But I'm here, and I'm delighted to be here. I'm sorry I missed the other solar symposia. So the title of my talk this morning, or this afternoon, would have been this morning, is Really High Efficiency Solar Cells. And I want to tell you about this is an exciting area that really derives its inspiration from some of the initial thinking about the thermodynamic aspects of photovoltaic energy conversion, which will involve light trapping, collimation, the impact of quantum efficiency, the influence of carrier thermalization. I'll talk about future efficiency targets. And this is an exciting field, and like many exciting fields, it's one that Eli's fingerprints are all over it. And so you'll see that as we go along. So I have a number of talented student and postdoc collaborators at Caltech who were part of the work, and then there's a very talented team at Alta Devices, the company that Eli and I founded now 4 years ago. And Eli's had, as you'll see in my talk, a significant influence on the work and the progress of the company. And I want to acknowledge also a team that I've collaborated with for a long time at the FOM Institute in Amsterdam, led by Albert Polman, and his team, which last summer actually included my son. So that was kind of fun. So when we think about photovoltaics, it's useful to go back to probably the first thinking about photovoltaic devices in thermodynamic terms from Shockley and Queisser in 1961 that thought about the energy exchange at equilibrium between the sun and a photovoltaic device. This is sort of the frictionless conducting sphere physicist's conceit for a solar cell, namely a sphere at 0 Kelvin surrounded by the sun. And a more realistic picture of a solar cell, which is a substrate at a finite temperature with a p-n junction that's illuminated by the sun, which subtends not 4 pi steradians around the solar cell, but in fact a small disk. The sun is not a laser in the sky, but it is a small light source, and therefore it impinges with a fairly collimated beam for direct sunlight on the solar cell. Of course, if there's aerosols in the atmospheres and there's multiple scattering, then we see a diffuse spectrum. And Shockley and Queisser looked at the central theme of their analysis was the balance between absorption and emission of light at thermodynamic equilibrium, radiation, assuming that incident photons would generate a single electron hole pair within the semiconductor. And from that derived many things. And they were able to account for many of the loss factors between essentially the Carnot limit, and I've made here a sort of a bookkeeping of the various loss factors. So if we start at 100% efficiency and we say that a solar cell is a heat engine, and the heat engine that it's operating in communication with is a 6,000 degree Kelvin black body, then the Carnot efficiency now brings you down to 93%. And then there are some other features that are difficult to get around, like the losses of energy in absorption, re-emission at the operating point. There's a term that's due to the reciprocal nature of beam propagation in optical systems. If we could develop non-reciprocal elements that would somehow accept light into the solar cell but prevent the light from escaping, which is not absolutely impossible, but it's difficult, then we would be able to gain back another 7%. Then there's this very large bar right here, which is due to carrier thermalization. That means the photon energy exceeding the band gap energy in the semiconductor. Then there are several contributions that are due to entropy losses related to increases in photon entropy. One due to essentially the difference in direction, the directional configurations of photons coming into a solar cell versus going out. A term due to incomplete light trapping. And then if you add up all those bars, then you can actually come down to find yourself at the ceiling defined by the limits for a conventional single junction solar cell that doesn't aspire to improve upon any of these opportunities for increase in efficiency that thermodynamics presents. And there are solutions that are in principle available. And we can, for example, there's been a tremendous amount of effort, and I know you heard from Shunwei Fan this morning about light trapping. And I'll describe things in terms of the local density of states. Eli has had an influential role in thinking about the local density of states and its influence on spontaneous emission. It also plays a significant role in solar cells as well. And we can also, I'll show you an example, we can do something in principle and maybe also in practice about the loss of angular information in solar cells. And I think we can do a whole lot more than is presently done about carrier thermalization. These up here are going to be harder. And if we think about the factors that I showed here at the bottom, other than the carrier thermalization, like we can express these in terms of a free energy associated with photons as they come in, are absorbed in a semiconductor, and if I have a semiconductor with a reasonable quantum efficiency that has a reasonable probability of radiative emission, then I can view this in terms of this exchange between absorption and radiative emission here in the energy level diagram across the band gap of the semiconductor. And I can frame this in a Helmholtz free energy picture, and I have the internal energy played the role of the internal energy for a photon absorbed at the band edge by either the photon energy or the band gap energy. They're equivalent without thermalization. These entropic terms here that are due to loss of information due to loss of directivity, incomplete light trapping, and also quantum efficiency. And if you go through and look at the logarithm of each of these factors and multiply by 25 millivolts, you can convince yourself that there's a loss here or an energy difference between the band gap energy in a semiconductor and the open circuit voltage here that now could be anywhere between 400 millivolts and maybe even a volt in a very low quantum efficiency material. So that's a huge penalty to pay in a solar cell, particularly if you have some prospect for improving and mitigating these loss factors. And this is not just theory. This is a plot here from my friend Richard King at Spectral Lab, in which he made a systematic study here. This is a plot of the solar spectrum. And this is the band gap of semiconductors, and then these points here are the open circuit voltages, and this is the band gap versus band gap unity slope plot. And you can see there's a systematic offset between the band gap and the open circuit voltage for a variety of high quality epitaxial single junction solar cells. Here, germanium, gallium indium arsenide, higher band gap gallium indium arsenide, aluminum gallium indium arsenide, gallium indium phosphide, aluminum gallium indium phosphide. And if you do that subtraction, you can see there's systematically an offset of about 400 to 500 millivolts that's coming from those terms. And so the first thoughts about how much light could be contained within a solid were actually in the statistical ray optics picture developed by Eli and his collaborators in the early 1980s. And this was framed in the ray optic limit and basically suggested that if you had scattering in such a way that all of the modes, the internal modes, radiation modes within a bulk solid in the ray optic limit and in the weak absorption limit could be populated, then there would be an increase in the intensity, and since the absorption scales with the intensity, of 4n squared. And I wasn't here this morning, but I feel sure that Shunwei Fan probably shared some thoughts about this with you. But it's an important step forward because it really sort of set the bar for what is the absorption in a semiconductor, and it represents an opportunity for not only the current, making sure that we absorb light and have enough photocurrent, but we also are able to improve the open circuit voltage. And so this now represents an opportunity to increase the photocurrent here, as shown prototypically for a silicon solar cell versus cell thickness. And you can equivalently think if you had a target of some photocurrent in mind, you could make the cell thinner by achieving full light trapping at this so-called ergodic limit, where all of the radiation modes are populated. And Shenwei also developed recently a model in terms of coupled mode theory, temporal coupled mode theory, that views an absorption limit in terms of the number of modes and the spectral bandwidth of modes. And if you use Shenwei's model in terms of discrete modes from coupled mode theory, you can arrive for a homogeneous dielectric medium with a refractive index n at exactly the same result as the statistical ray optics picture that Eli developed in the early 80s. But what's interesting is what happens when you now go into the wave optic limit, where now the waves that are propagating through the material are not all plane waves. And in some cases, these waves can be highly confined. So for example, if we have a wave in a low index material that would have a low light trapping intensity factor due to its low index in the bulk, if that mode is highly confined near a high index material, like a metallic mirror, and say trapped in between that high index metallic mirror and a high index cladding layer, then the effective mode index, the waveguide mode index, can be considerably higher. And then this light trapping factor now has a factor here of 4n squared lambda over the waveguide index. And so this guide index can become very large, and this factor can now, in principle, exceed 4n squared. And so Shenwei described an example, and the most expedient examples are ones for which the bulk index is low, like in an organic semiconductor, where cladding with high index materials can provide the biggest boost in mode effective index in that waveguide. So recently, our group took a slightly different picture. It's all related in the end, but it's also useful to think in terms of the electromagnetic energy density, in terms of what we call the local density of states, the density of modes that are present at any given particular point within the medium, times the mode occupation times the energy per photon. And when we think about the local density of states for a homogeneous material, you have this Rayleigh-Jeans type expression for the local density of states, and it's the same as the density of modes uniformly throughout the material. But now when you get down to the wavelength scale, this local density of states becomes inhomogeneous, very inhomogeneous. And on the next slide, I've shown here what the different structures for which the local density of states can be extremely inhomogeneous, such as a silicon thin film, and you can convince yourself that if you calculate the integrated local density of states in a silicon thin film, it's always less than the corresponding bulk silicon, which is a sensible result. I can't occupy as many modes in a thin film where I've constrained the number of modes as I could in the bulk. But now if I clad with a metal, I find that the density of states, local density of states at a metal absorber interface, if this absorber is an absorbing dielectric medium like a semiconductor, or a metal dielectric metal absorber metal structure, this can be enormously greater than for the semiconductor alone, and as much as 1,000 right upon the surface plasmon resonance of this structure. But for example, for this metal insulator metal structure, it also has a very strong non-resonant component. So this leads now, and this is familiar in terms of the dispersion relation, to essentially an index that you can infer from the low group velocity in the material. But so you can say, well, okay, this is interesting, but it involves metals. Metals are lossy. Are there any dielectric materials that have this property as well? And indeed, you can also see this same sort of phenomenon with an enhanced local density of states for a low index medium clad by high index non-absorbing dielectric surroundings. You can also, for example, tailor the local density of states in photonic crystals and achieve considerable increases in the LDOS relative to a homogeneous bulk of the same material. And then the final example is that of an optical antenna, which is an object that's received a lot of attention. In fact, Eli himself is actively working on optical antennas at the moment. And you can find that within the gap of an optical antenna, you can also have this enormously greater local density of states. So I would suggest that these are all motifs that you could think about for greatly enhancing the local density of states, the absorption, and then also importantly, the spontaneous emission in these kinds of semiconductor structures. And the spontaneous emission is important because if we're not working with semiconductors for which this quantum efficiency is high, then it's well known that a low quantum efficiency emitter in proximity or in an environment with an enhanced local density of states can have a higher radiative rate, and its effective quantum efficiency can go up because the local density of states affects the radiative rate and not the non-radiative rate. So this is well known from LEDs and fluorescence in biological systems, and people working in plasmonics know this very well. But this also confers potentially a benefit for low quantum efficiency semiconductors, low internal fluorescence yield, meaning low radiative to non-radiative rate ratios, and could potentially add some number of KT to the open circuit voltage of a solar cell. So that's something that has largely been unexploited to date. Our group has also been spending quite a bit of time looking at small metal objects as, in terms of their strong scattering and mode localization for localized surface plasmon modes, and also waveguide modes that take advantage of the fact that these metal objects have a very large and negative real part of the dielectric function, permittivity, leading to strong scattering by metals. You also have to worry about the loss, of course, of metals. But of course, in a solar cell, many times you have to have a metallic contact anyway, so you might as well use it to your advantage to enhance the light absorption and mode excitation. So Vivian Ferry, who actually was a student in our group and is now a postdoc here at Berkeley, developed an array of pattern structures to enhance the mode density in thin film amorphous silicon solar cells, shown here, and showed that both the short circuit current and the spectral response of such a pattern structure could be significantly enhanced relative to that of a flat solar cell, but also significantly enhanced relative to that of a randomly textured cell. So commercially, cells are made on roughened glass substrates made by Asahi Corporation, the same company that brings you Japanese beer, that are coated then with silver to form a back reflector, something that looks like this. And this is a full-wave simulation of such a structure here, a randomly textured glass surface coated with silver, zinc oxide, PIN amorphous silicon. And what you find is that this random texture is non-optimal for the balance between parasitic absorption in the metal and scattering into the semiconductor. You find that these sharp asperities here give rise to localized resonant modes in the metal, loss in the metal. A more gradually curved structure, which you can achieve by nanoimprint lithography, now provides very strong scattering, but less parasitic absorption in the metal, and enhances the photocurrent of the thin film amorphous silicon solar cell considerably. In fact, this thickness here, 90 nanometers, is 1/3 the thickness of a conventional amorphous silicon solar cell, and achieves near record. The world record for a single junction cell is around 10.2%, and the highest we achieved was 9.6. So this brings me also to light management in another context in very high quantum efficiency semiconductors. And this now is where the story intersects, where Eli and I have intersected most strongly in recent times. Although I have to say, I first met Eli, you probably won't remember this, when I was 22 years old. And by my calculation, that means he was 35 when I was a graduate student at MIT. And it was memorable for me, and we had, and I'll tell you at dinner about some of the things that influenced my career in the work on solar cells. For one thing, he helped provide the inspiration to sustain us over the 20 years when nobody cared about solar cells. So, and that was a great thing. And finally, Eli and I got together and managed to convince some people to care, and formed this company called Alta Devices that makes thin film gallium arsenide solar cells by epitaxial liftoff. And here I'll pass around these cells that when they're peeled off the rigid substrate, they can be put on, they're extremely flexible with a metallic backing. These are cells made for gallium arsenide. These are single crystals of gallium arsenide. I think that's an unprecedented size for at least in conventional thinking for a solar cell. And these cells have routinely efficiencies in the 25 to 26% range. But so I think Eli recognized that this is certainly not the limit for efficiency. And in particular, for solar cells that have a very high internal fluorescence yield or internal quantum efficiency, high ratio of the radiative to the total emission rate, the spontaneous emission inside the semiconductor, the absorption, re-radiation, gives rise to what we call photon recycling. So in the circumstance where you have a very, very high internal fluorescence yield or quantum efficiency, plus a very highly reflecting mirror, the photon is recycled many times. It could be as high as 100 times before it's extracted. And Eli recognized that this was an opportunity, and he also recognized that it was very important, harking back to Shockley and Queisser, that it was important to emit the light, that without paying attention to the external fluorescence emission, which is a necessary balance to the absorption, light would not be absorbed in the cell. So in fact, the maximum efficiency is achieved by maximizing the external fluorescence emission yield, leading to his now oft-repeated mantra, a good solar cell is a good LED, a great solar cell is a great LED. And this led to some spectacular records that were set by engineers at Alta Devices. It's actually one of my former students who was the person who led the team. But Eli provided a lot of tremendous insights as to how to optimize cell efficiency. And a world record was reported at the PVSC, Photovoltaic Specialist Conference meeting last June. And in fact, the record has now been broken several times since. And in fact, it not only broken, I guess in the current vernacular, five minutes, okay, shredded by a good more than 2 percentage points over the most recent record 2 years ago. And here, Eli and I are holding a 22% efficient module. This is a world record efficiency thin film module. So one can also think about attacking the problem of the angular emission by providing collimating structures. If we could restrict the angle of emission, a thin solar cell could have it that has a Shockley-Queisser detailed balance efficiency in gallium arsenide of about 33% without angular restriction, could go over 40% for perfect fluorescence yield. Okay, if even gallium arsenide is not perfect, at 90%, which is achievable in gallium arsenide, you can still get very close to 40% efficiency when you restrict the angle of emission down to a few degrees. So you might ask, well, is this very practical to do? Well, we decided to see if that was possible using microphotonic structures, and these are structures that were written. These are compound parabolic concentrator structures, a curvature that has an optimal curvature for directivity and concentration, and then we produced these structures by 2-photon lithography, drilled a hole in the bottom with fib, and use these as light directors. And this is a full-wave simulation of light being directed out of such a structure. And this shows the transmission through an aperture, a bare aperture with no light director, and an aperture with the director showing the influence of collimation. So we think this is in fact possible. You can actually build whole arrays of these structures and build these as a sort of microphotonic layer on the surface of a solar cell to enjoy this efficiency benefit. And so just before quitting, I should mention that the biggest bar on the chart is the carrier thermalization loss. And to attack that, we think that the most interesting thing to do is to reduce this defect between the photon energy and the band gap energy by making not a triple junction solar cell, but by making something like an 8 to 10 junction solar cell. And we think that will be the future. We think it should be relatively straightforward, provided we can build a structure that efficiently splits the solar spectrum. Each of these acts essentially as an array of single junction solar cells on a circuit board. And this just shows the arrays. You can calculate the arrays of band gaps and spectral widths. It's a beautiful engineering optimization problem. And you can go back to detailed balance calculations and convince yourself that with modest concentration, you could get well over 60% efficiency in such a structure. So we think there's a new range, a regime of photovoltaics at hand in the 50 to 70% efficiency range. That this is really the target we ought to be aiming for. And so the scientific tools that will be needed to get there will be to control light trapping in the local density of states, to achieve very high internal quantum efficiency, to control the emission angle, and to minimize carrier thermalization. If we can build these nanostructures that allow us to do this at large scales using, for example, printing methods, I think we can really drive photovoltaics to grid parity with unsubsidized cost and true energy supply significance.
Any question or comment?
So you mentioned you could use high Q. to help with low quantum efficiency materials to effectively boost their quantum efficiency. How do you see that playing out, though, with needing broadband absorption across the whole frequency range? Because the high Q would seem to contrast with that.
Well, so what's important is high QE, I would say, not high Q. Something like the metal insulator metal waveguide structure has a large local density of states that's non-resonant. So the effective Purcell factor across the whole visible and near IR is between 40 and 60. So you have to worry about the losses, but something like that. I think it's possible to build waveguide structures rather than resonator structures that don't have narrow resonances.
I have a slightly different question from different aspect. We know that many, in nature, many photosynthetic complexes, that they're very highly efficient. Why it becomes so hard when it comes to artificially make some photosynthesis systems? And I just want to know your opinion about going into that direction.
Okay, well, so I think what's efficient in natural photosynthesis is some of the internal energy transfer processes, the Forster transfer processes between the sort of antenna molecule and the molecule that does the redox reaction. But the overall system is very inefficient, less than 1% efficient in terms of going from photons to chemical fuel. At Caltech, we have a very large project underway called the Joint Center for Artificial Photosynthesis in collaboration with Lawrence Berkeley Labs to greatly improve that photosynthesis yield way beyond 1%. So some of those internal steps are efficient, but the overall photon efficiency is low.